1, 2, 3. Okay, good. Right. Hello, everyone. Thanks a lot for showing up at this talk because it's at the very end of the conference, so I'm pretty surprised that someone's here. Anyway, let's talk about macros in Scala. Just a quick show of hands. Who here knows about Scala? Has coded something in Scala? Whoa. Okay, that makes my job much simpler. Anyway, so my name's Eugene, and I'm a compiler hacker. As you can see from the stats on the slide, I really like hacking the Scala compiler. Uh, I did a lot of experiments there, but my biggest passion in Scala C is macros, and that's what we're going to talk about. So in today's talk, we will take a look at the design that we shipped with a production version of the compiler, a design of compile-time metaprogramming via macros that marries metaprogramming and types. Then we will take a look at what's the best thing about macros and what's our worst nightmare. And finally, as promised in the title of the talk, we will see what we're planning next for future metaprogramming capabilities in production Scala. All right, so without further ado, let's begin with a really quick tour of our metaprogramming capabilities. Well, the Scala Macros project, it started as my PhD project. So every time when someone comes to APFL to join the doctoral program, they have to do a semester project, essentially. So at that time, I knew close to nothing about Scala, but I heard of this esoteric language called Nemerle. This is one of the less known languages on the .NET platform. And it had macros. They fascinated me a lot. So luckily, luckily there was a chance to take macros and just implement them in Scala. The thing is that just right at the time when I started at the PFL, our lab and TypeSafe, well, Lightband, now called Lightband, the company that does commercial support for Scala, they started a joint project that was about building a native data access library for Scala. One of the key features of the project called Slick was language integrated queries. So language integrated queries, also commonly abbreviated as LINQ, it's a common idiom of encoding data access via by allowing users, by allowing programmers to write queries to data stores as if they were writing, normal higher order functions like map, filter, group by, and so on and so forth, using the usual capabilities of the language, such as lambda expressions, as we see on the code example above. And then, thanks to LINQ, there should be some kind of a way of turning these queries into a structured representation that can then be operated in domain-specific fashion. So here, in the example on the slide, we see how the natural-looking code users.map and then some lambda gets transformed into some representation of the query that can then be transformed into SQL or what have you. So in order to implement that, we could go ahead and use the experience that has already been explored in C# and F#, declare that that parts of Scala syntax that need to be transformed into this domain-specific representation, we declare them as some sort of expers, as shown in the example here on the slide. And then the compiler, every time when the user provides a value of type t, and the value of type expert of t is required, the compiler would magically transform one into another. So that's how it worked in C#. It worked very well, but we decided to take one more step ahead. So since we are going to operate with syntax trees in the form of expert, why not go and execute inside the compiler, where everything is represented as a tree and, well, types, symbols, but trees are the main thing there. So while we are executing inside the compiler, we could also gain some other very useful properties. For instance, we could do early validation of these queries and then report potential errors faster. So now, since we decided to adopt this particular design, the main question is, how does the compiler figures out that when the user writes users.map, that it needs to invoke the meta program written in macros.map at the very top of the slide? So in order to do that, we declare users.map as a macro. So here's how a macro declaration looks in Scala. At the left-hand side of the macro declaration, to the left of the equals sign, We see a regular type signature. So this is how one declares methods, normal methods in Scala. So we have a type parameter called u here. We have a term parameter called fn. We have a normal return type. So everything is usual. But on the right-hand side, the macro definition, it has a reference to a macro implementation, which is the meta program that whose sketch we've seen on the previous slide. So in that meta program, we take something called context, which provides an entry point into the reflection API, into our meta programming API that macros can use. And also this meta program, it takes an abstract syntax tree representation of its argument. Finally, it has to return another abstract syntax tree that will be inlined at the call side after macro expansion is finished. So inside this meta program, we can call arbitrary Scala code. So nothing, there are no limits at all. We can do IO, which allows for some really crazy stuff. And we can also call arbitrary functions that are written in some libraries. So here, for instance, in the example, the translate function that we're called, we assume that it's defined elsewhere. So we can just take normal Scala libraries and then call them from macros. Finally, execution of the macro, it typically finishes with a quasi-code. That is a notation that allows easy creation of abstract syntax trees. So here we can see how the macro creates an abstract syntax tree that corresponds to creation of a table. Then we create some domain-specific object called map, and finally we integrate the dynamically calculated value into the expansion. So now let's see how the expansion will look like. Let's take the code at the top of the slide that the user writes, users.map and then some lambda. And then after the compiler encounters invocations to table.map, which we declared as a macro, it will invoke the associated meta program that we've seen on the previous slide. And then finally, it will inline the results of that meta program, that is the macro expansion, into the call side, achieving the desired result. So just to sum it up, to sum up our really fast tour of Scala macros, here's the full code example that we just explored. So obviously the function translate is declared elsewhere because it wouldn't fit on the slide, but otherwise the example is more or less complete. So I think it's a really good time to make a pause and take questions if you guys have any. All right, please go ahead.
Why does a map need to be in a separate macros object instead of right on the right hand side of the equal sign?
That's a very good question. Yes. So the reason for this is more of a social one than a technical one. So I remember the keynote that Bjarne Stroustrup gave here at Carrion a year ago, and there he said that for some language features that he was pushing, when these features were sufficiently alien to the current mindset of programmers, people insisted on very loud syntax. So here, the design that we see here, we should view it through the lens of that time 5 years ago when macros were introduced. So macros were really the first of their kind of a feature for compiled and metaprogramming in the official distribution of the language. So therefore, we really considered the opportunity that people will get confused, and so we decided to explicitly spell out that, this macro, it takes a context, and then fn is actually not a function but an abstract syntax tree, and it returns an AST as well. Yes, please.
Speaking of C, why do you call these things macros? They work on syntax trees. You don't have any syntax bugs.
Yeah, sure. That's an excellent question. Indeed, there was some controversy around this name, but personally I decided to call them macros because in Nemerle, things that did similar stuff were called macros. And in Nemerle, I guess, they draw inspiration from Racket, which we also did, by the way. So that's a very brief story of the name. All right, any other questions? Yep, please go ahead.
Why is it C.tree rather than just tree?
Wow, that's an excellent question. I'm really glad that you spotted it. So if I were to introduce that, it would take a while, but now I'll just provide a very brief explanation. So actually, the reflection API that macros work with, it's very unlike usual libraries that one can see in C# or Java. The thing is that all the entities that macros operate with, like trees, types, symbols, what have you. We have like a really big API. They are declared inside this, inside the big thing called universe, inside an object. So since an interesting feature of Scala is that it allows to nest classes, types, whatever really, inside other classes, inside other values. So due to some very interesting pattern, which is called cake pattern. You can Google it later. It would be really hard to explain it like on the spot. The Scala compiler is written in a very peculiar style, and so we essentially took compiler internals. We took the way how they were written, and well, more or less copied it into our API. I will talk about this later, maybe in like 20 minutes. Okay. Anything else? Great. Let's proceed. So the best thing about Scala macros, what's so cool about them? Something that I promised earlier, probably that caught someone's eye. Well, actually, after the public release of macros that happened in Scala 2.10, they spread around the ecosystem like the wildfire. So a lot of popular libraries, they're using macros. And well, you don't have to trust me on that. You can go to the website of Lightband, the company that does official support of Scala, and just check out their Lightband stack. So everything there, it either has used our stuff or they have experimented with it. So why did this happen? Why macros were so popular? That's a very good question, and probably part of the answer it's social again. But speaking of technical stuff, I think an important feature of macros is that they can transparently enrich the familiar concept of a typed method call. As we've seen on previous slides, I'll probably go back there. Macros, they look like normal methods. So here, users of table.map, they don't even understand that table.map is declared as a macro. When something misbehaves really seriously, they will of course deduce that. But in the normal mode of operation, everything will be fine, and they won't even understand that they're using advanced language features. And as a result, people have been able to use common library writing idioms to incorporate macros and then enrich them with additional capabilities. So now, in order to provide an illustration of this very abstract concept, let's take an example. So here we see a fragment of a REPL session that tries to format a string. So here we take form a string in the syntax of Java. So this .format method is actually defined in the Java standard library. And then we try to pass a string to a format string that expects an int. So unfortunately, Scala's type system isn't powerful enough to type check the string and then report the mismatch at compile time. So we get a runtime exception from the JDK. So actually, with macros, there's no such problem as the type system that's not powerful enough. So here, I'm exaggerating a little bit, but just a little bit. So here we can see how the custom string interpolator, this f thing before the double quotes here, is able to take the format string and then at compile time figure out that there's a type mismatch between the thing that we're trying to format and its format specifier. So now let's see how this example works out and how we would be able to implement this feature ourselves if we wanted to. So first of all, let's see how string interpolation works in Scala. We were talking about feature interplay between macros and other stuff. So let's take a look at some Scala features. So string interpolation, here we can see another REPL session. It works in a pretty straightforward way. In this case, we have a string interpolator called s, which can take variables from the lexical scope and then splice them into a given format string. As a matter of fact, when I was calling string interpolation a feature, I didn't mean that it's like a full-fledged feature which is handled very, very specially by the type checker. As a matter of fact, it has a simple desugaring. So here, the s interpolator that we see above, is actually desugared in the call to a method s. That's done on something called string context, which is a standard type from the Scala library. And finally, this method s, it takes a the things that we're splicing in as arguments. So that's pretty straightforward desugaring. And it's important for us to know that string interpolation is not something magic. It's actually equivalent to this code as if we were writing it ourselves. Now let's see another feature called extension methods. So how does this how does one declare custom string interpolators if they're represented as calls to the standard method called to the standard type string context? Well, in Scala we have support for extension methods. So mind this heavyweight syntax, please. This implicit class is something, but in any case, there's a way to enrich the public API of a given type with some additional methods. And this is how we do it. And if we declare method f like this, to be an extension method on string context, which is provided as a parameter to an implicit class, then the string interpolation f hello world will work fine. And now here's the beauty of macros. They naturally integrate into this picture, and they allow us to introduce compile time checking into this pipeline. So if we declare this f extension method as a macro, then the compiler will transparently rewrite the string interpolation into the invocation of the f method, and then once it encounters this invocation, it performs macro expansion. So in this case, you can see the results of the macro expansion at the bottom of the slide, and there the macro doesn't have to do anything special. It just creates temporary variables with specified types that it infers from the format specifiers. And then the code that we've erroneously written, it wouldn't even compile. So that's how we get this pretty error message that we've seen before. Type mismatch, we provided a string and actually int was expected. Yes, please. Wow, a lot of questions. I'm very glad.
So what is the location of the error?
That's a very good question. So I didn't want to talk about that in detail. So again, some very brief explanation. Actually, macros, they feature an API that can specify positions of customer error messages that they're emitting. And in this particular case, if we take a look at the expansion, this API is not even necessary. Because here we see some synthetic code, val arg $1, for instance. But this synthetic code, it also includes real code. For instance, x, it's taken from the program as it's written by the programmer. So in this case, x will be the culprit of the error, and therefore the type error will be positioned at x. So everything will work out magically, but of course in real life sometimes things, they do not do that. And for these cases we need an explicit API to position errors manually.
Can I override existing functions with macros?
Yes and no. The
I have a specific question. Suppose I have a function f that goes from some type a to b, but if I happen to know the actual value of a, I might be able to say b prime, which is below b. Can I override this f with a macro so that if I see this particular value of a, I get a better type?
Right. Okay. So first of all, since macros are expanded at compile time, no virtual dispatch is possible. So the normal notion of overriding that we have in Scala, it's not applicable.
That you can do any, you can compute at compile time anything you want, including I/O, for example, or probably capturing a continuation and whatever. Mm-hmm. That's it. So you yes or no?
All right. So as I said, the short answer is no. This is the answer that I would have provided on the forum. But the extended answer is yes, because macros can do anything. So theoretically, they can take a look at the program and decide what to do with it. Yeah, sure. So by normal means, you cannot do that.
What's non-normal means? I need to know. I need related work.
All right. If you insist, but
yes, I insist.
I didn't tell you that. So actually, as I mentioned before, macros, they're using this wonderful context. Here it is. See colon context, and the context, it somehow encapsulates the magical world of the reflection API. And so this magical world is actually the full Scala compiler. So with some downcasting, you're actually able to get a hold of the compiler itself. Oh yeah, of course. That's very nasty, but I warned you. Yeah, how cool is that? Okay. Any other questions to this particular example? Who knows how many revelations are waiting? Well, anyway, so we've seen how macros interact with existing language features, namely string interpolation and extension methods, to achieve something that wasn't possible before, in arguably quite an elegant way. So actually, there's a bunch of other examples of feature interactions, of positive feature interactions. Thanks to macros, we've been able to implement quasi-quotes, these Q quotes that construct abstract syntax trees that we've seen before. We've also been able to implement async and await, not as a language feature, but as a library. So that was a project performed by TypeSafe, now called Lightband. With macros, it's naturally also possible to do deep embedding of DSLs. That is, take some fragments of Scala code and then imbue them with custom meaning. There's also type class derivation, which is similar to deriving in Haskell and Rust. And Heather, my colleague from PFL, she's been able to implement a really fast serialization library based on that technique. And finally, with these macros that we've seen before, we've even been able to emulate type providers. That's one of the crazier things. So if you're interested in that, please find me later. I have a lot of interesting stories. Anyway, but now we really have to proceed in order to feed this talk into the timeline.
And I have one more question before you go on. Can you override function application so I can turn a strict application into lazy application? I mean, you already have by name, but can I automatically insert by name before you actually run the program in function applications?
All right. So again, the official answer. So the official answer would be, in order not to confuse those who will be watching this talk later, is that macros, they expand locally, which means that if we have a function, a method application, this method is a macro, then the macro, the fair game for the macro is only take a look at the application and then replace the application with something else. Oh yeah, of course. And this crazy stuff with compiler internals, well, jokes aside, it's going away. It's not like we're very fond of it.
But I cannot define apply as a macro.
Oh, you can. Why not?
Does that do what you just asked?
No, the standard function application cannot be overridden with Java. That's what it's saying. But you can rewrite other applies into the lazy.
Yeah.
Yes, that's right. So in Scala, it's possible to define methods with hard-coded name apply that will be invoked when something is applied to something else. So if you explicitly define this apply as a macro, then you can control what happens there. But standard functions, like function one and so on and so forth, for arity of the arguments, they apply is a normal method. Yeah. So therefore, it's off limits officially.
I can't implicitly do everything.
No. All right, so now that we know the best thing about Scala macros, and it's not that you can do everything there, it's that you can do stuff in a principled manner, hiding behind type signatures and local expansion. Now let's take a look at what was the most complicated in our macros. Well, when I was preparing for this talk, I actually took a look at GitHub, and I estimate that the amount of effort that it took us to get there, it was about 1K commits, probably a bit less. And the accumulated changes, lines of code that were changed there, they were like in thousands of, hundreds of thousands of lines of code. Yeah, that's a lot. That's a lot, I know. Now let's see why it took us that much, right? So actually made the list a breakdown. So first of all, macro engine. It's actually the simplest thing that we have. So as I suppose, as one may suppose, it contains some tricky logics. It took us a while to figure it out, but all in all, it's just a couple K lines of code. The second thing that took us a lot of time is, of course, discussions. It's not there in the lines of code size, but it's there in man hours, man years, so to speak. Another thing, it took us even more time, is to build the community. So as I said, macros were the first of their kind, and therefore the target audience for them when they just appeared, they were just a dozen of people who've written Scala compiler plugins before, and now we needed, of course, that was too little for a feature that was to become part of the official Scala distribution. So therefore, we had to create the community. It took us a while, and now what was the real thing there is the reflection API. So as you can see from here, in the final incarnation, it's almost 10k lines of code, and plus a bit more of that for documentation. It took us several rewrites, and now you can start to understand where this 100k lines of code came from. So reflection API, that is, if you have any questions, then I would be glad to answer. Embarrassed. Okay. Well, this sometimes happens. Anyway, so this Scala Reflect thing, we actually needed to provide some sort of an API to macro writers, an API that they could use to throw together abstract syntax trees, destructure them, ask them for types, ask types for lists of members, and well, this basic stuff. It took us a while. And now we get to, the worst thing about Scala macros, which is how we did that exactly. So as I mentioned before, we took compiler internals, and then we exposed them behind a very, very thin abstraction layer. It was a cool solution, the coolest thing that I ever did in my life. So we were very agile. We could deliver this thing almost immediately because the compiler, it already implements all the reflection APIs that you need, and even more, of course. And then for power users, those dozen of people who wrote compiler plugins before, we provided Paradise because they could downcast to compiler internals and then do even crazier stuff. But the only downside to this plan, it was that this thing, it required a little bit of learning. But man, I mean, Scala users, they're pretty smart, right? They will get it. Well, what could possibly go wrong, right? And naturally, that was the reaction of the community when we unleashed the macros on them. Well, jokes aside, let's see what exactly went wrong. I can talk about this for hours, but here I will give just 3 reasons. Well, first of all, since compiler is a very complicated beast, and now its history, it counts more than 10 years, it contains a lot of stuff, and therefore we had to expose quite a bit of that stuff so that we can get the basic operation going. As you can see from this list, there's a lot of different kinds of trees. There are types, symbols, also scopes, names, all these big, nasty, complicated ball of classes. It's hard, so just explaining this, it takes a while. I'm currently finishing my thesis, and well, it takes a while. That's probably the biggest problem here. The second problem is that the Scala compiler, and in particular the Scala's type checker, which runs macros, it has this nasty habit of doing desugarings. Well, desugarings, they're a very nice textbook technique to implement languages, as we all know from textbooks. But unfortunately for macros, if we do desugarings pretty liberally, like here, then the innocent-looking code on the top, it will turn into the monster at the bottom, which is kind of crazy. And the monster at the bottom is what macro writers have to understand in order to write macros that take things on the top. So this kind of breaks the intuition and the what you see is what you get feel that we want to give to macro users. Unfortunately, well, that's the case. And with the API that we get from compiler internals, we cannot do better. And finally, we just locked ourselves in by exposing compiler internals. Because, we prevented the evolution of the compiler. I know of a few pull requests that had problems going in just because they changed the API that macro writers grew to expect. And also, there were problems with tools. So the compiler, it naturally implements the interface required for its internals. But other tools, going ahead and implementing those hundreds of methods that we exposed, well, that's not a good idea. And as a result, as a very practical result of this kind of theoretical question, there's an IDE in our community which cannot expand macros just because it's built on a different type checker. That's fairly sad, I would say. Of course, some there's a good point that counterbalances it all. Since macros in Scala they hide behind type signatures, so macros look like methods, which means that they have typed parameters and they have return types and all that. We can approximate the behavior of macros with these type signatures. So this IDE is of course not completely useless, but there are some problems with certain corner cases, and that's definitely unfortunate. Well, since there's a problem and I'm giving a talk here, well, I have a solution already. So let's see how we figured out what to do with the situation. Since the reflection API was so important to our macros, we decided that we will start from first principles. We will design this a better reflection API from scratch, and then once it's ready, we go ahead and use it to build better macros. What happened afterwards, after this realization, is that we created a new project called Scala Meta. Recently, we had the version 1 release, which is a really clean room implementation of the language model. So it models all the definitions that the language has, all the possible terms and types, all this boring stuff. And since Scala Meta cannot depend on anyone, it cannot depend on the existing compiler or on the IDE that implements its own type checker, we had a problem. So it took us a while. But the good thing there is that we didn't have to conform to any limits. We didn't have any limits essentially. So we designed our abstract syntax trees to be really cool. That is, we didn't do any desugaring. So the desugaring from one of the previous slides, it's not a problem for our parser. And also, we didn't throw away any information about the code. So Scala's batch compiler, it's famous for throwing away white spaces and comments because who's gonna need them when our goal is just to produce executable bytecode? But of course, if you do metaprogramming, if you're writing tools, this kind of information is important. So we could not do anything with that before, but in Scala Meta we retain all this information. And finally, as I mentioned, Scala Meta was designed to be platform independent from day one, which meant that we're really targeting all the tools. We want the macros that are written against Scala Meta to be executable everywhere, not just in a particular compiler. So just a few examples. So that's how we comprehensively model Scala syntax. So previously we've seen how this for comprehension it gets desugared into something. So on the top part of the slide we see how Scala reflect our current API process it, and at the bottom we see how we process it in Scala Meta. And also speaking of syntactic details, so in that example above, we see how the Scala compiler drops the comment as something that doesn't matter, and in Scala Meta we somehow retain it. The mechanism how we achieve that, it's probably too involved to go into it right now, but please contact me later if you're interested. And you know what? Since we spent so much time working on this good ASTs, once we were finished, we realized that it's not about macros anymore. It's not about just macros anymore. Because thanks to these ASTs, people have been able to implement tools that weren't possible before. So here's two examples of our earliest adopters. First, we have Codacy, which is a web service to do style checks on code from GitHub, Bitbucket, and stuff. And so their Scala engine, it uses Scala Meta to provide users with the capability to write their own rules. And thanks to the fact that Scala Meta can model Scala syntax comprehensively, as shown here, the rules can be very detailed. And secondly, there's a very cool tool that was developed recently by my master student, Olaf Gerson, called Scala FMT. So Scala FMT, it takes the comprehensive lexical model provided by Scala Meta. It takes a look at the tokens that comprise the code and then formats them accordingly. And as I mentioned, now the tooling story is at least as important as macros to us. So we have a lot of cool ideas and are now working on them. So hopefully I'll be able to report on that in future conferences. Now back to macros. Let's see what we did to macros once we had Scala Meta. So now I'm not going to present the final result right away. We'll just go through the design process that we had. So yes, the mandatory disclaimer. So this thing, it hasn't shipped. So everything may be changed. Please don't rely on that. Well, that's really necessary, based on my experience. Anyway, let's start with the current macros that we've seen before. So this thing table.map that calls a custom meta program, and then try to cut the boilerplate first. So as mentioned before, it's really unnecessary to split these macro definitions and macro implementations. So this code in blue is just pure boilerplate. We cut it out since people now have understanding of it, and we just merge the code. And now what we do next is we try to unhard code some of the special cases that we had before. So previously, this separation between macro defs and macro impls, it's a really textbook illustration of how not to do language design. Because this thing that comes after the equals sign in the macro definition, namely keyword macro, then white space, and then some very, very specific syntax that the compiler expects there. It's very error prone. So it's unlike everything that's there in the language, and it requires the user to specify to follow some particular rules that are there just for macros, for nothing else. So now let's do this analysis on on this on this design that we've arrived. So what we can cut out from here and what we can replace with orthogonal parse. So first of all, the left-hand side of the macro. As we've seen, everything's fine with it. It looks like normal method definitions in Scala, so we have regular signature, so nothing has to be changed. But this right-hand side, which says macro something, it's kind of weird because, well, macro is a keyword which is used just in this particular language feature. Can we do better? Let's try to take a look at this block of code in isolation. And actually, if we like really squint, I don't have much time, so I'll go through this a bit faster. Then this block of code, it does make sense on its own. So if we try to think of what it does, then we can view this macro block as some sort of an indication to execute this block at compile time, take the results, and then inline them at the call side. So here we don't have macro expansion. We just have a facility to invoke custom code at compile time. So that's a pretty cool language feature that was just born from macros. So if we try to play with this feature a little bit, just take this block, assign it to a variable, or pass it to some function, everything looks fine. So it looks natural. And what we finally need is the ability to deliver these macro blocks to call sides of macros to achieve feature parity with the previous functionality. And for that, we introduced a modifier called inline, which says that the method, it has to take its right-hand side, substitute parameters with actual arguments, and then inline the result to the call side. So here's how macro expansion works in this new world. It works in 2 steps, actually. So we take the right-hand side of the macro, because the macro is declared as inline, and then we get the intermediate result, which is just the macro block. Finally, we do compile time function execution of this block of code, and we arrive at the final result. So now with a slight rebranding with a slight change from macro to meta, just switching the keywords around, we arrive at the design that we plan to pursue further. So this is pretty much the good old thing that is already in production and that people grew to like, but without the boilerplate and without hard-coded definition syntax. So we're really looking forward to exploring this design avenue, and of course I would welcome your comments. But since I'm running out of time, we'll have to do that afterwards. Finally, just to conclude, macros, they ended up being a powerful and popular feature in Scala. The best thing about macros is that they combine metaprogramming and types and transparently enrich existing language features. The worst thing about macros that we went on about in details is that the metaprogramming API has proven to be inadequate, and it provided a really high barrier to entry. Finally, a much better metaprogramming API is already in the works, and it turned out to be about much more than just macros. So we're really looking forward to the future of our new metaprogramming world in Scala. Thanks. Okay, so I think I cannot take any questions now, but
Let's take 2 questions.
2 questions, awesome.
So over many years of experience in scheme and racket, we've learned that phase separation is important. Do you do any of that?
So phase separation and hygiene, this is something that we're really
I
looking
only asked
forward
about
to.
that one, but
Yeah.
somebody else can ask about the hygiene.
So long story short, we did not yet get to that.
Okay.
So we have, well, we don't have phase separation. Essentially, whatever side effects you do at compile time, they will be shared between macros. But of course, they will not be carried to runtime because Scala is a compiled language.
Right, but then you can sort of observe what your units of compilation are and stuff like that.
That's right. It's nice, so we would like to do better.
Okay.
If there's nobody else, I will ask. Anybody else? So you can't be as unsurprised that you were missing good macros in Scala. Now you have mediocre macros. Congratulations. But I have a question about the language community. This is a social process. You clearly have a lot of code in macros 1.0, right? And you're introducing a whole new way of doing it. Are you splitting the community, or are you deprecating? Technically speaking, are you deprecating the old stuff? And in terms of community, did you answer the question already? Oh no.
No, no.
And in terms of community, do you expect people to really follow the deprecation, or are you going to split the community into the novel power users and the people who got used to the old stuff and want to experience more pain, or whatever?
All right. So of course, it's I think the most important question of software evolution. The goal of macros was always to be to work in the production environment, and I think that's the most important question of those. So, as you can see from this example, this is the new macros. The code that is used there, it doesn't it doesn't call any fancy APIs. So it just uses quasi-quotes to construct abstract syntax trees. It calls into some custom logic, but all in all, it doesn't do anything involved. So this such macros, they will be trivially migratable to the new system because you just need to merge macro definitions and macro implementations, which were previously split, and then you can use quasi-quotes which behave almost like the quasi-quotes of version 1.0. Of course, power users that were downcast into to compiler internals and trying to do crazy stuff, we won't be able to support them. Unfortunately, that's a non-goal because we allowed too much, and now we're going to suffer for that. Well, it's not like the original macros that were using too much of the compiler internals API are going to disappear. Authors of these macros, they can always write compiler plugins that implement similar functionality. So as I mentioned before, that's one of the good things actually that we use the compiler internal API, because everything that was written in macros, it can be like copy pasted into compiler plugins and it will all just work. It's definitely very sad. Please don't think that I'm taking this lightly. That we exposed a huge API and now we just cut it and enjoy it. No, we do not. We'll try to do as much as possible here. All right, the third question. Can we take it as well?
I see that function translate must. I see that function translate must look at all fields in table U. It's possible really now, or it's just ideal example.
Could you reformulate?
I
I'm not
see
getting
that
completely.
function translate.
Yes. So translate.
Yes.
It takes an abstract
From
syntax
T
tree.
to U,
Mhm.
yes. I guess that translate must know about type about T, must know declarations in T.
Yeah.
Yes.
Probably it does. Yes.
Yes, and is this really work, or it's just in a cloud example?
Oh, it's possible for the function translate to take the abstract syntax tree, then to ask the compiler for its type, and then to deconstruct this type and figure out the exact values for T and U.
So we have some analog of reflection.
Yes, definitely.
And it's work now.
Yeah.
Uh,
Okay. I guess we're out of questions. Thank you.